Hello, everyone. Please bear with us another couple of minutes, and we'll be starting shortly as we're admitting other participants to the webinar. We will be starting the webinar in a minute or two, so kindly bear with us. All right. Good morning, everyone. Thank you for your patience. There's always that group of people that comes. All right. Carlos, just hang in there, yeah. Just get a
Sure,
bunch
no
of people
worries.
better than not miss that first moment. All right, perfect. We'll kick it off. So, hello everyone. My name is Gabriel Grubach. Very happy to be here for the 11th special geothermal talk. It's been an effort that we've been doing for a while now. I would like to briefly show you that. And this, please let me know that you can see. Carlos, can you confirm?
Yes, all good.
So I just wanted to give the audience a little bit of background. What the special talks really are is an effort from now, a lot more sections than when we started. We're 12 now. And I'd like to thank SP Aberdeen section for joining us recently and Stewart support in this. We have done, as you can see on the list, quite some interesting talks with some really involved personnel in the geothermal world and the oil and gas world. And the idea behind all this really was to educate the public, right? But also to keep strengthening the ties between oil and gas and geothermal, because there's a lot that we can learn from each other. And this has turned out to be a good way of doing this, right? As you can see, there is a link here, the YouTube link that I will put after in the chat box, and you can access it there, and you can go back and watch all the other talks that we did last year. We did all the way from geothermal in Croatia to the body heat project to percussion drilling, a lot of interesting topics. Without further ado, I would like to introduce our speaker today, Carlos Granado, who's got quite some extensive experience in reservoir simulation. And initially, when we had a talk with SP Spain, whom I would like to officially thank for making this happen, the question we asked is, what are the topics that are of interest? And reservoir modeling, trying to understand the reservoir, is one of those things, right? We're all aware what goes in comes out, garbage in, garbage out, right? But being aware of all these kind of things, it makes you think, what is the quality of data that I'm using to build the model? What am I trying to find out? And what do I do with it? Essentially, do I save money? Do I develop the project the way, that it was initially planned? And Carlos has been very kind to join us here. He's got extensive experience with CMG for the last 20 years. He's been on the business development side of the company, and recently said he's going to make some changes and moving. So we wish him luck with that. I would ask the audience that if you have any questions, please put them in the chat box. And at the end of the talk, we will take the questions and we'll have Carlos try to answer those questions. Without further ado, I'll pass it on to him. Carlos, please feel free to share your screen.
Excellent. Thank you very much, Gabriel. Give me a second here. There are so many screens right now. And okay, here we go.
Yeah,
you see that?
It's all good. Yes.
Excellent.
Perfect. Thank you, Carlos.
No, thank you. Ready to go then?
Ready?
Okay, good. Well, thank you very much for the opportunity of being here, to SPE, to Gabriel, to Sonia. I'm really glad, and it's an honor to me to be presenting to you about what we have seen as an experience in geothermal reservoir modeling. We're going to start the presentation with some important. Give me a sec. This is not moving. Okay. Some sort of important facts to discuss, you know, energy transition. Give me a second, I'm trying to. Okay. Energy consumption, we know, is by far the biggest source of human-caused greenhouse gas emissions, responsible for at least 80% of the worldwide emissions. Within this energy sector, particularly heat and electricity generation is responsible for at least 38% of these emissions. CCS has been largely implemented in many projects in the US, Europe, and Canada, but this process is about disposing CO2, which is already in the atmosphere, but we need to stop producing CO2 in order to reduce the emissions and to get to the zero emissions by 2050. In one hand, the director of the International Energy Agency ascertained that the world is set to add much renewable power in the last 5 years that we did in the last 20. Some experts predict that by 2028, almost 42% of the world electricity is going to be coming from renewables, particularly dominated by the solar sector, of course. Due to the pressure on decarbonization, government seems to be changing policies and you know, backing up a lot of projects in order to reduce the cost of some of the most known renewable energies in order to allow them to emerge. In an international agency report titled Renewables 2022, energies review energy resources around the globe, it finds out that the wind and solar outputs are expected to account for 90% of the global expansion in the coming future. Regarding the power capacity growth over the years, we have here the plot that shows that in 2022 was another record for installation of zero carbon power generations, the technologies. In geothermal, not necessarily the same, but solar, we can see that in the right side of the screen that added over 180 gigawatts of energy compared to the previous year. Geothermal capacity grew a little bit, but it wasn't as expected as it was not for 2021 or for 2022. And the fact that 90% of this expansion is basically located in the US. You know, for the fact if you compare the amount of dollars invested in geothermal compared to other renewable energies, geothermal had like something close to 10 billion US dollars, while solar and wind got over 140 billions each. So the questions here arises, and why is geothermal energy has not been developed? We kind of compare, or some experts compare geothermal to what it was cell phones in the 90s. They were really big, expensive, and only few people could have them, but it has drastically changed. So we think that this is going to be the case for geothermal, and only in the US, geothermal offsets emission of 4.1 million tons of CO2 in the atmosphere. So this is certainly an important renewable energy to account in order to get to the zero emission to 2050. 2050. Okay. So maybe it's the time to start talking about the agenda. We're going to be going into the introduction of geothermal energy. We're going to be looking at some specialized geothermal examples. We're going to be creating a basic geothermal case in order to show how easy it could be to generate at least the initial stage for modeling the geothermal in a reservoir simulator. I'm sure we are already aware of what geothermal energy is. It is a type of renewable energy taken from the earth core. It comes from the heat generated during the original formation of the planet and the radioactive decay of the material. This is a naturally occurring source of renewable energy. As we know, the mantle of the rock named magma gets to some spot close to the surface near the crust, and this typically happens near tectonic plates boundaries, which are the areas where mostly of the volcanic and earthquakes activity happen. When the magma comes toward the crust, the rock and the water absorb the heat and create the geothermal reservoir, which are the basis of our activities for developing the energy. This map from the National Ocean Services show the hot spots and how they are located to of course the close to the tectonic plates, to the boundaries of the tectonic plates, and it's not a casualty that most of the geothermal plants are located close to these spots. This might end up changing in the future since we are kind of in the era of applying geothermal everywhere. So this is a part of the discussion we're going to be having today. Let's talk a little bit about the advantages and disadvantages of the geothermal energy. Maybe this is the reason why the geothermal hasn't been largely developed. Geothermal has a huge potential. The current consumption is around 15 terawatts in the world, which is far from the potential of this energy. The geothermal resources right now, the installed capacity is like around 17 gigawatts, which is represented 5% of the total potential. And of course, we're trying or governments are trying to increase the amount of geothermal, and by reducing the cost, guessing the potential for generating energy from enhanced geothermal in US is about 100 gigawatts, which is 25 times what we currently have, and we could be energy to at least 100 million American homes. It is obtainable and stable. Geothermal provides a reliable source of energy compared to other renewable resources, such as the wind and the solar. This is because the resource is always on. It's basically 24/7, 365 days a year. It doesn't depend in any conditions on like the wind and the solar, so it's really obtainable and stable. It is reliable. The energy generated from this source is easy to calculate, since that not fluctuate in the same way as other energy resources. It means that we can predict the power output from the geothermal plant with a high degree of accuracy. On the other hand, we don't need to invest in any technology to convert this energy, or either to storage in big batteries or fields or anything. So this also has an advantage. It has been having a rapid evolution, as we said before. There is a great deal of exploration into geothermal energy currently. It means new technology are being created to improve the process and to reduce the costs. With this rapid evolution, we expect to have a growth of the increase of the geothermal capacities from the current 70 gigawatts to perhaps maybe 50 gigawatts into 2050. I still think this is conservative, but anyway, what happened in the last 2 years shows that we might be delayed a little bit in the implementation of this technology. Within the challenges of this technology, of course, well, it is expensive. The total installation cost is usually between 2.5 to 5 million for a geothermal power plant of a megawatts generation. The exploration and drilling, of course, it play a big role in the cost. It's around always the 30% of the cost of the project. The drilling of the wells and the water production of the project will indeed cause some changes on initial conditions from the reservoir where we're injecting. And these changes could change stresses or changes of stress causing, maybe surface, not only surface to change, but also maybe the cap rock failures or reactivation of big faults that might translate into earthquakes. We have some cases in Germany and New Zealand that the stress on the injection of the fluid could reactivate faults and earthquake happen. So we need to be aware of where we're injecting, how we are changing the conditions of the reservoirs in order to avoid impacting other areas, okay? We have the possibility of creating thermal short circuits. Even though it is a sustainable and a renewable energy, the changes, the locations or the reservoir might cool down after a time, making it impossible to harvest some more energy. So we need to account for the resources and be sure that we are taking into consideration all the uncertainties in order to guarantee that we have a long-term project in the future. Like in the oil business, geothermal reservoirs needs a specialized subsurface know-how to guarantee that the proper management and monitoring to enhance the operations decision to procure the long-term success of the projects. So far, we could classify the reservoirs in 3 types. We have the conventional geothermal source that we call it, which is more similar to ONG's reservoir. You could have a fault or a fracture rock, which you could inject or produce from and obtain the heat out of or the energy out of it. It requires to have faults and fractures and some permeability in the reservoir and also water in order to be able to obtain the energy. The second is different because in the second there is no permeability and there is a possibility to have no fluids in it. So you need to create the conductivity by creating the permeability by fracturing the rock and injecting fluid from one end and producing it in the other. So this is called enhanced geothermal system. There is an important amount of uncertainty related to it because we don't necessarily are aware of the stresses on the formation because these are basically unknown formations, and we need to account and be sure that the way we are fracturing and the way these fractures are behaving guarantee that the project is going to be viable. So this is a big uncertainty to account for. The third category, this is the most developed scenarios in the last years, is closed systems. Especially, it consisted in recirculating water from one end of the reservoir to the other end of the reservoir through vertical injectors that maybe connect in a bunch of multilateral wells in the bottom of the reservoir. It works like a big heat interchanges of radiator. And we need, of course, to clearly have the understanding of what's the impact of the rates of the water on the exposure of this water and the time of the exposure of the water with deformation in order to understand which is the amount of heat we can or the energy we can get out of this interaction between the water and the exposure of the water with the heat formation. And this is important to account doing maybe reservoir simulations as we are going to be talking about. Let's go and jump directly into the risk factors that involve the geothermal. We have, of course, a bunch of factors that affect or create risk into the project. We have the political, we have the regulatory that are usually, insufficiently and contradictory, and we have some weak legal frameworks that doesn't help our case. We have the financial risk also because it depends on the markets that might be fragmented, inefficient, and suffering from currency fluctuations. So at the end, the resources are not necessarily there. We have seen, as I mentioned in the beginning of the presentation, and we already know that some companies have been benefit by some of the programs that have been launched by the U.S. government, by the Department of Energy, particularly with this geothermal power airshot that is looking for the reduction of the cost of the enhanced geothermal technologies to around 90% of what they cost right now. This is gonna largely impact the possibility or the feasibility of the application of this type of projects in other part of the world. We're gonna be focusing here basically in the technical risk of the process, which is our main area of expertise. We need to understand the uncertainties present in the resources to account for them and to account for the capacity of producing energy. It also accounts for the optimal number of wells, the potential, economics, the time of completion, the field development plan, operating strategy in order to guarantee the long-term success, similar to what's happening in the oil gas. So for that, we need to consider what are the physics, what are the parameters we want to grant in order to make these projects long-lived. Okay, so talking directly to the physics involved in the geothermal reservoirs, well, we have many sites and companies should account for this technology and to technologies that account for all these physics in order to provide and to represent each of these phenomena to grant somehow the correct representation of the processes. Let's start with fluid flows in the porous media. Important, most of the flow in the geothermal reservoir occurs in natural fractures present on the formation or generated in the igneous rocks due to the thermal stresses. Permeabilities are very small in this rock, but still might account for some flow. The correct representation of the flow in the fractures and the matrix is really important to accurately represent the physics of the process. Heat transfer, conduction, convection, dispersion, counterflow of the steam and water, whether the geothermal system is natural or man-made, heat transfer is the most important phenomenon, and it will be critical to evaluate the amount of energy that you can obtain out from the resource. This type of production strategy optimizations are really important in order to get the best out of the resource regarding the energy. I'm sorry. Heat transfer, of course. Heat pressure losses, I'm sorry. Wellbore pressure and temperature calculations are critical to estimate the correct and optimal conditions that should exist to guarantee the minimum losses of energy when the producing fluid from the geothermal reservoir get to the wellbore. Geomechanics, of course. Geomechanics are really important in order to consider when implementing this type of projects, not only for the impact it might have in the activation of faults or subsidence, but also the impact of fracturing the rock to enhance the communication between injectors and producers. Many of these resources have not largely developed. Stress are, as I said before, unknown, and estimations based on analogs might need to start with the evaluation of uncertainty assessment to guarantee or to quantify the risk associated to the process. Thermodynamics, of course, very important, not only for representing the water properties such as viscosity, density, and these changes when it passes through different phases from supercritical conditions to liquid due to changes on pressure and temperature. Also, water chemistry plays an important parameter, since different reactions might occur during the process, and depending on the mineralogy of the water, some scales might be present on the systems, and these deposits might affect not only the flow in the tubings and the facilities, but also into the reservoir. for the risk in the geothermal project, we need to, take into consideration well of operation. Drilling cost is between 30–50% of the total development cost of the generation of the project. And this is why it is so important to account for the uncertainties present in the reservoir to evaluate the optimal number of wells, their location, the design, the operating conditions that might yield to have a successful or a failure in the process. If drilling is successful, then the reservoir must be tested in order to determine the magnitude and the productivity and the expected longevity of the projects. It's only after that you can, size your design of the plant and the facilities, and then have the understanding of the capacity of the resource in order to generate electricity. And this is something that you need to account after you at least tested the reservoir, okay? The selection of equipment, hot temperatures, abrasive rock, corrosive environments, located deep underground, come with a significant unknowns, as we know. Many high temperature resources are highly aggressive brines with a high contents of total solids, and bring a lot of other problems that might affect the facilities, not only corrosion, the position. So this all needs to be properly accounted in order to be able to represent correctly what happened in the reservoir. So after we have kind of a talk about the physics, the phenomena, the risks that we have to overcome in order to implement this type of processes, I would like to go directly into the specialized geothermal samples that I prepared. Let me just go directly into our. I'd rather to do this directly in our preprocessor in order to avoid, passing or make it more interactive. So I'm gonna just go directly into the cases I have prepared for you. The first case is a standard geothermal case. This consists in the completions of various production wells out of a geothermal reservoir. In this case, we not only account for the location, the completions, of the type of completion and the spacing between the wells, but also the possibility of having the cool down of the formation, or maybe the increment of the productivity of the energy by inputting some injector wells into the system. So I'm going to show you more or less the impact of having this. As we see here, we not only account for the spacing, but also a very important thing to model is the type of configuration that we're going to be using in order to produce the water. In this case, we add different type of isolations into the system, and also the different tubings and configurations in order to see what was the best way of achieving the best temperature from the perforations into the wellbore. As we see here, we also added some injecting wells into the case of a study. Give me a second. Reason necessarily. Give me a sec. Give me a minute. Okay. So right here, I'm gonna show you, sorry about that, I had a crash, and I'm gonna show you how we can see our original output for the energy was shown in the black dot, while we were just injecting, or we just producing without any optimization on the locations of the well. The second case, we try to just, come up with a better configuration strategy and completion configuration in order to have the highest temperature on the reservoir. And the final stage, we kind of include some injectors wells in order to increment the potential of the energy. And we see how we can increment the energy of the project in almost 30%, which is a big change compared to what we originally had. This is why it's so important to generate some, optimizations out of these cases in order to represent the correct, to optimum strategy in order to obtain the maximum advantage of the resources. The second case we're going to be presenting is an enhanced geothermal system, as we said before. There is a large uncertainty to account when we do this kind of evaluation, because first we need to fracture the wells in order to create conductivities between the injectors and the producers. And we need to account of what happened not only with the water and the rates that we're going to be using in order to allow the water to expose to the heat of the formation and interchange heat, but also to account for what happened with these fractures once you start injecting water. The thermal stresses are going to cause that the fractures kind of open a little bit more because of the injection of the cold water, and the compaction of the rock is going to open the fractures instead of closing it, as we see in the oil industry, and it's going to create some preferential path for the fractures to go to allow the water to go directly from the producer into the injector. So we use we use this technology in order to represent the unconventional reservoirs in general. We model the fractures by using what we call a tartan grid, or a logarithmic scale local grid refinement. And with this technology, we guarantee that we can represent the behavior, the exact behavior of the fractures and effective permeabilities of the fractures from one well to another. In this case, we were able to optimize the optimum spacing. We can see here, let me stop a little bit. This is two horizontal well, one horizontal well in the top and one horizontal well below. And as you see, if we get the wells too close, then we have the risk of having the water travel directly through the fractures from the injector to the producer, not having enough exposure to heat, and also it end up cooling down the formation inside. So what we do here is we kind of optimize not only the rates, not only the completions, but also the spacing between the wells. And we accounted from the fractures property changes during the process. And with that, we managed to kind of to increment somehow the production from at least the temperature of the production water in 15%, which is an important advantage compared to what we originally estimated. Let's go into the third case. Third case is a closed loop U-shaped wells geothermal. This is interesting because at the end, as I mentioned, these are big heat interchangers, and the answer to the question to be answered here is, what's the distance? What is the length of these wells? What is the distance between them in order to avoid cooling down the formation and having some kind of short circuits, thermal short circuits? In this sense, we perform some simulations where we can actually we are able to represent the U-shaped wells in the simulator. And you can see them here graphically. With this, we create sensitivities on the distance, the length, the rates that we are going to be using. But the most important thing to show here is that if you compare the simulations between the results between having the wells located at 20 meters, 40 meters, or 60 meters, it has an important change on the performance of the temperature, especially because when the wells are too close and the formation start cooling down, we end up, presenting. I'm gonna move forward to the end, so we see the results at the end. We see that with 20 meters, basically the formation is cooling down. The whole surroundings of the well is cooling down after 10 years. Same happened when you have 40 meters. But when you have 60 meters, it's granted that the heat of the formation keeps heating completely the surroundings of the well, incrementing the temperatures of the head of the reservoirs in around 15%, which is an important change compared to what we originally get. The important thing here is that there is technology that allows you to represent the U-loop. I mean, this is not an easy task to represent that from one end you are injecting, for the other end you are producing, and what happened in the between. This is hard work to achieve, but technology has taken us to be able to represent this type of completions, and it's available for the public. So it is interesting to have. Another case that we can discuss is about the, calcium carbonate case. As we know, there is a lot of carbon dioxide in the present, and when you have geothermal fluids. With the pressure drops, the chemical equilibrium of the ground changes, and some of the CO2 might release into the gas phase. This process generates kind of super saturated calcite that will start depositing not only in the tubings but also in the formation, and this might end up affecting the flow on our system. Now, of course, affecting the amount of energy we're gonna get out of the reservoir. We generated a case of a study using the results of calcite, the calcite deposition or generation by modeling the autoclave experiment into our simulator, and then taking it into the full field case. We can see here that after we complete the well and we include the calcium carbonate precipitation inside it, we can see that on time, we see some solid concentrate increasing in the system. As the result of that, the hydraulic diameter, effective diameter of the tubings start being affected exponentially. And due to that, if we do a comparison of what would be the results by not including the chemical reactions or the calcite precipitation, we can see that we estimate a completely wrong way of producing the energies. When you start representing or including the calcium, the calcium carbonate precipitation inside the system, we see that the reduction of the oil rate because of the reduction of the hydraulic diameters of the tubing. The interesting thing here is we use our optimization tool in order to find the optimum rate that allows us to produce the maximum amount of energy without causing the reduction of the deposition of the solids. And we found out by just reducing the liquid rate in the system in 20%, we managed to avoid the precipitation of the solids inside of it. So this is another case that might show that the simulation might end up saving a lot of time and efforts before the implementation or the calculation or estimation of what we're going to be producing or getting out of the resource. Another interesting case that I wanted to talk about was the thermosiphon. Thermosiphon is a combination of geothermal energy with CCS. Basically, we inject CO2 into a saline aquifer, and then we use the CO2 in order to be the fluid to extract the energy out of it, using CO2 as a surface fluid to extract energy has several advantages over water and brine, as it has much lower kinematic viscosity than water and brine, and the mass flow rate through the reservoir is higher than when you use water or brine in order to get the geothermal system. So the most important thing here to start is the generation of the CO2 plumb. The generation of the CO2 plumb, during this time, the CO2 is injected into the reservoir to displace the brine, and that is in the production wells, and it kind of create a CO2 plume, or what is called. This stage is crucial because there need to be sufficient amount of CO2 in the reservoir to minimize the water coming out of the production wells before the production commences. So basically, during this stage, you want to displace the water out of this configuration of wells in order to allow the production of CO2 to be higher than at least 92-94% compared to what you produce in water. So the optimum point at this is to have water a saturation of gas at the producers that is over 60% compared to the saturation to the original saturation. We can see here in the two plots, in the right side, in the left side is temperature. You can see how the CO2, once it gets injected, it gets heated, but also you can show you can see in the right side of the screen how the saturation of the gas end up being close to 60-70% close to the wellbores, which somehow granted that the formation of the plume is correct and that the water is displaced out of the producers. The CO2 plume formation is a case, is a lot of discussion about that because it depends a lot of permeability, porosities, and also, you know, the configuration of the wells. But at the end, we are trying to model here what would be if it's possible to implement this type of project. If we see here, we end up doing sensitivities on the closure time of the producers, and we see that with closing, I mean, keeping the injection and keeping the producers well shut for 2 years, granted the water is displaced out of them, and the production of CO2 and being over 94%, which is good enough to grant the project. On the other hand, the temperature is sufficient in order to grant that the temperature is going to be the flash of CO2 in the surface is going to be generating the power for the turbines that are going to be used, and then can be re-injected into the reservoir again after the process is completed. The last case is not a developed case, but I just wanted to show you that there is the technology in order to implement this type of very complex loops. This is a case of a configuration of a well, of 6 pair of wells, where you inject on the top of the reservoir, or the top of the top wells, and then you produce into the connected wells that are below to go to the surface. It seems to be a very complex configuration for modeling, but we have managed to kind of represent it into the simulator. And at the end, we can, you know, grant that we are able to represent the process. We haven't optimized this case. This is an original state, but the thing that we wanted to prove is that it is able we are able to model somehow these type of complex configurations for further investigations. So now that we have basically finished the cases of studies that I wanted to share with you, I'm gonna just give you a quick shot of how we could generate an easy model from the scratch. The idea here is to show that you don't need to be an expert in modeling or geothermal in order to generate at least the initial stage model to start working with. So I'm gonna be using it's not a matter of doing any commercial, you know, publicity or anything, but this is a tool that I have available, and I just want you to show you that there is a technology that is advancing together with what is happening in the field in order to be able to represent and model whatever we are applying in the field. I'm gonna select the simulator, the thermal simulator that we use. and a year of start, just to generate the single model, okay? We have a possibility of generating a model straight from the scratch by just using a process wizard, where we have used this process wizard in order to generate several types of enhanced oil recovery processes, but in this case, I'm gonna model just the geothermal case. When you click here, you kind of have an explanation of what is the geothermal, what we aim to do with this wizard. We're gonna skip that, and we're gonna just go into the geothermal options. Here, we have the possibility of generating a closed loop geothermal, injecting a producer and an injector in the same well, annulus and tubing, or we could do a U-shaped well. I'm gonna go for the easiest case, which is just, injecting from the tubing and producing from the annulus, or vice versa. Once we open the wizard, basically you don't have any grid, you don't have anything. You just can, select whatever you want here for the properties of your model, permeabilities, porosity, size of the grid. If you want the grid to go into the top of the reservoir, and just to account for the losses of heat in the wellbore from the bottom to the surface. So we're gonna say that to generate the model to zero to the sea level, okay, to the top level. I'm gonna just add some permeabilities, very low permeabilities, in order to represent a real system. I'm gonna just, use a reference depth of around 2,500 meters and an initial reservoir pressure of around 24,900 kilopascals. You can set the thermal conductivity of the reservoir zone, the overboard and the underboard, and you can change that if you want, if you have the data. If you don't, you can use whatever we offer here as a reference. You can add or not isolation into the system. I'm gonna put some isolation. You can actually select the sizes of your tubing or the annulus and just input them. Or you just select them out of the API table that we have here. I can select one. You can select the gradient of the temperature. I'm gonna just put here 20 degrees as a Celsius for the temperature at the top of the reservoir. If we finish, then basically you have your model created. You can go into the section of the wells and see that you have created somehow the tubing and the annulus properties, the thermal conductivities for the system, for the tubing and for the casing, and the diameters and the isolation that you have generated. We can go and select in our reservoir grid. Let me go and go into the 3D section so you more or less see what we have generated. Right here, we can, just delete the grid and create some transparency. And voila, you can, see here, how the grid size are really low in the reservoir, and then from the reservoir to the top, you have larger grids because you just want to calculate the losses. And we can select the modeling of auto tune in order to use artificial intelligence in order to increase the simulation. And we can just run the simulation as it is. So we see the initial results. We run the simulation as it is. You can see this is running already. We are injecting the water that we selected to be injected. And I guess this is gonna take like 10 seconds to run. Okay, running 18 seconds. Let's close that. Let's go directly and see the results of what we got. We can see here that we have just generated a closed system easily from the scratch. We go back to the initial result. We can see how we can, see we are injecting a water, cold water, and when it goes down to the system and it gets exposed, it goes up again, and we end up producing, a water of around 70 to 75%, 70 to 75 centigrades at the top of the reservoir. It was really easy to, to set, as you saw, and I just wanted to show you that it's not that difficult to generate that geothermal case out of scratch with the current technology. So let's close the presentation with the conclusions. For sure, geothermal play a key role in decarbonization to reach zero emissions target. New technologies are improving to overall cost effectiveness of the geothermal energy. Current technology grants the possibility to model most of the geothermal configurations. Geothermal simulations can optimize projects to increase their long-term value. So this is it. Thank you very much.
Thank you very much. Thank you so much for this insightful presentation. You actually showed a lot of things that personally and some other people around me were a bit surprised that these things already exist out there, at least the ability to model some sort of it. And I'll tell you that the chat box is full of questions. But before we go there with the audience, if you don't mind me, we're going to run a very quick poll. And it would be very nice if you answer to that question, because we're trying to understand what is the SP versus non-SP member ratio in these talks. Essentially, we are looking for a 50-50 ratio, let's say, mix, because that is the whole idea. As of now, we have answers coming in. I am going to end the poll in 10 seconds, so please vote. This is important to us and for the future webinars as well. All right, so the vote is there. I'll share the results. So 66% of the audience here are SP members, but 34% are not SP members. So that's great to see. We'll keep doing these and keep connecting the two worlds. I am going to jump straight to the questions, Carlos, if that's cool with you.
Yep.
The first question is, we've had a lot coming in from Bob Pearson. Good to have you here today, Bob. So he said, Carlos, how do you represent, this is a very good question, the proppant distribution in the fractures in the LGR with relatively uniform horizontal stresses in granite and little leak off? It is likely very different than in a shale frac.
Yeah. Well, basically, we model that via, we don't have the possibility of representing the proppant distribution. Well, we do have, but I haven't included in these particular cases. We can basically cause a reduction of the permeabilities of the fracture depending on the stresses if we want, and we can actually change the permeabilities from the initial part of the fracture into the tip of the fracture in order to represent the changes of the permeability due to thermal stresses. I don't know if this answered the question.
He will let us know in the chat box if you did. That was interesting to know and hear that you do have some sort of capability to do that. Bob actually followed up with a question saying, does your geochemical model, is it able to model silica dissolution and redeposition in the EGS fracs?
Yes, it is. It is basically we are able to represent the whole process of redissolution and deposition if we want to.
Great. That's a straightforward yes. Marius Nitzel coming in from Austria. He said, any recent technology advancement in your field of expertise worth mentioning that enables geothermal energy? This is a bit of a broader question.
Yeah, well, basically what we were trying to show here is that we are developing our technology based on what we see in the field applications in order to be able to give an advantage of the results and maybe to help users to reduce their uncertainties before even going into drilling and doing a pilot. It is a way of you know, somehow making sure we are going toward the safe area once you want to implement whatever you are planning to implement into the field before investing a lot of money into it.
So you're enabling by basically taking out a good chunk of the risk in a
Exactly.
sense, right?
I
Thank
would
you
say
very
so.
much.
Yeah, I would say so.
All right. We have a question from Amir. He said, once injection and production is started, how important are full field simulation models and what do you history match?
Well, right now, in geothermal itself, with so much so new in technology, we could, if the field has some data, we could model basically the temperature profiles along the wellbore if we want, the rates, the pressures if you have them. Mostly in green fields, what we try to implement is to understand what happens if you change something, what happens if the fracture has different property, what happens if you inject the rates, what happens if you change the isolation. But if you have all that data, basically you can use whatever you have, temperature and rates in order, and wellhead temperature in order to history match what you already have as a project, you know?
Okay, perfect. So it's also a bit of a dynamic, it's a dynamic process per se.
Yeah.
For those that do history matching of fractures, they definitely know what that's about. Bob comes in with another question. He says, does CNG have a frac model, or are you importing the frac dimensions and conductivity from a third-party frac design model?
We have the, thank you, Bobby. This is a really interesting question. We have the possibility of generating the fracture system directly in our simulator if we want, by using the methodology of the tartan grid that I show you in order to represent what is the stimulated volume and the fracture volume. And we can also input the data out of the third party tools, you know. It depends on what the client wants.
But a follow-up to that, Carlos, if you say you can model fractures, does that mean you have a fully coupled, fluid and proppant transport model in it?
No, I model I model it via effective permeability of the fracture, okay? Modeling explicitly the fractures using the tartan grids. You can actually import the fracture of the third party, and we can also have the possibility of modeling directly the fractures as a separated node in order to model the opening of the fracture and the closure of the fracture using the geomechanical tool if you want. But this is a really more complex than the original, point that I discussed in the presentation.
Yeah, we've done this in the past quite often. Take third-party fractures and then just import them into a simulator, which tends to be pretty good, let's say. Another one from Bob: can you import a nonlinear geothermal gradient in the well model?
Yeah.
Straightforward, yes.
Yes.
Marzia Kamali asks, for solid deposition, should we define the reservoir fluid with specific components and then use the wizard for calculation?
No. For deposition of the fluid, we use the autoclave results. Basically, we have the changes of pressure and temperature and the deposition of the calcite in an experiment. We model that into the simulator, and then we scale that into the full field model.
Okay, thank you, Carlos. Agustin Alario says, have you tried to incorporate in the simulator a discrete fracture network? Great question. In order to better capture the flow between fracture and matrix and how it compares with regular local gridding refinement option results.
Yeah, we have both options. We can have a discrete fracture network or use our tartan grid methodology. In this particular case, we haven't tried, that I know, a geothermal case using the discrete fracture network, but we have the possibility of doing so. So if the client has the network generated, we can import it into the simulator and have it work the same way we did with the tartan grid. Yeah,
that was actually a great question, right? Because of the way it affects essentially the whole process of the geothermal. Bob is asking, is this tool available for short-term rentals and or as a consultant service or only as an annual tool rental subscription?
No, well, I don't know. We can talk about. You can
Yeah,
contact me
well,
later on to talk about that. But yes, there is a possibility. You can do consulting. You can rent it. You can do whatever you decide to do.
you will
It
find
is
a
it's a
solution.
commercial version.
As a matter of fact, let me tell the audience, we will be sending this recording to you. I will be emailing it out to you, and we'll put Carlos's contact there. So if you wish to pursue this opportunity, then you can go from there.
Mhm.
Um, Andrew Sims says a closed loop system with CO2 as the heat transfer fluid is effectively a big heat pump if operating conditions are right. Could you model this?
Well, basically, at this point, we haven't done the complete loop of the representation of the CO2 into the plant. This is not something that we have accounted with. We just managed to get the highest amount of temperature and the formation of the CO2 plumb in the reservoir to grant that you are getting to the plant the CO2 at the highest temperature and with the less amount of water, which is the aim on the reservoir point. We didn't model the whole system itself.
It sounds to me like once everyone gets your content, you'll be getting a lot of good questions to work on. There was a comment that came by, and it's actually a very good point. So part of these talks, they were generated and driven by the SP sections in Europe generally, but we've been having the support from the geothermal technical section in SP, and then there's the hydraulic frac technical section. So these sections tend to work together well. As you've seen in this presentation, deep geothermal, EGS, fractures, all that gets put together, and we have to work together for advancement per se. Thank you, Bob, for bringing that up. Juan,
Yeah.
is asking, where in the world are application of the CO2 plume?
Well, I don't know if I could answer that. There is a public information about that. I don't necessarily feel
Yeah,
comfortable with talking about
let's
where.
not do this. We'll have Juan look it up. Juan, you're gonna have to look it up. We gotta respect here the confidentiality. So we'll move on with Bara. Bara asks, thank you. Oh, well, it says, thank you very much for an interesting presentation. How to integrate these modeling approaches with 4D seismic data?
Well, that's a good question. I mean, basically, what you intend to incorporate when you include the 4D seismic is the changes if any properties can be connected to the changes of any attribute. So I guess this is a matter of just generating the property that you believe is gonna be changed because of the attribute that included into the simulation. I don't see any limitations for doing this. Actually, I think it would be awesome to try to include this data into it.
Perfect. So that's a positive answer right there. Thomas Franson says, thanks for the great presentation. And you've shown 3 geothermal, the conventional, the enhanced, and the closed systems. But what about to produce and maybe even inject into fractures with high perm areas?
Yeah, well, it could be close to what the standard geothermal is. As a matter of fact, you are not fracturing; you are just using the permeabilities or fracture of the that are already exist in the system. So we could account for that as a standard geothermal case, which is similar to what is happening in Cornwall in UK. Basically, you are using the formation permeabilities in order to flow from one injector to the producer, which could be seen as a standard geothermal case, no, because you are not causing those fractures,
It's a pretty straightforward case, right? Because you could be just
Yeah.
dynamically changing the permeability, right, of the system. Or okay, so it's very feasible.
Yeah.
Katarina says thank you. She enjoyed the talk. Thomas comes back with on top of heat simulation, does CMG carry example? Very good question. Lithium and predicts dilution versus time.
I'm sorry, it got a little bit.
No worries. I'll repeat the question. So,
Yes,
on
please.
top of the heat simulation, does CMG carry, for example, lithium and predicts dilution versus time?
Yes, we can do it. Actually, we can represent. We have some cases where we represent the lithium into the system.
Nice.
So yeah, we can do that.
So actually, to the audience, we are working on maybe next or the talk after. We will be working on geochemistry or geothermal. but we're planning to get
That's
a
great.
lot more in detail with it, right? Because we're extracting heat, but then there's other things that we can extract. So we're going to try to get into detail with that. Thank you a lot for that
Yeah.
question, Thomas.
Yeah. As a matter of fact, we have some cases of a study where we represent the amount of lithium that can be extracted out of the geothermal fluid.
Nice. So Juan says all the petrophysics are obtained by coring the wells where it has been feasible to log them.
I am lost. I mean, I'm trying to read because the sound is terrible, Gabriel.
So can you hear me now?
Yes, right now, yes.
Yeah. So it says the petrophysics is obtained by coring the wells, or it has been feasible to log them. Is it logging data?
Well, that's a good question. That might be answered by some petrophysics expert at this point.
Okay.
But anyway, the information that I use here is directly a petrophysics interpretation generated into permeability and porosity. I don't necessarily I'm involved in the generation or interpretation of the petrophysics to generate the properties itself.
Photoperm relationships, absolutely. And there's a lot of logging tools out there that will start slowly dying at those temperatures, which is what the industry is also working now in terms of, heat resistance. Bob says, in your Tartan LGR, do you represent unstimulated areas between widely spaced cracks as original rock properties, or a change in the average properties of the LGR?
No, we represent both. We represent the both areas, okay? The unstimulated area and also the fracture zone itself,
Okay, thank you. And then we come to the last question. I think Bara was just clarifying. It says, thanks for your answer, Carlos. I meant if CMG has any integration for 4D seismic generally or for geothermal?
No, it's just, I mean, we don't actually, as I said, we don't necessarily connect the geophysics information into the simulator. We just use the interpretation of what these 4D interpretations give us as a property change. Right now, we don't connect actually the geophysics directly with the reservoir simulation itself, okay?
Understood. Thank you, Carlos. I think we came to the end of the questions. I would like to personally thank you in the name of all the 12 sections in Europe that organized this. This has been a great presentation, great questions. Letting the audience know that I will be sending out the recording so you can always access this back. You have the YouTube channel where you can go and watch the other ones. Keep an eye out for the next one, because we're gonna look for geochemistry and geothermal and a lot more than that. So thank you, everyone, and see you on the next one next month.
Thank you very much, Gabriel.